Hi, welcome back to the Alkene Addition playlist in organic chemistry. In this video, we're going to go over a very important type of reaction for synthesis called hydrohalogenation. Okay, so for hydrohalogenation, you're going to use basically an acid that is whose conjugate base is one of the group 7 anions. So what does that mean exactly? Well, if you look at group 7 on the periodic table, what you would find is, remember, if you go across, it goes boron, carbon, nitrogen, oxygen, and then fluorine, where this is in group 7 over here. And as you go down the periodic table, you have here chlorine, and then you have bromine, and then iodide, okay, or iodine. Now, whenever these molecules, right, or these atoms right here get incorporated into their corresponding acid, you would see acids like this. You'd see hydrofluoric acid. You would see here's hydrochloric acid. You also have hydrobromic acid, and then the other one is hydroiodic acid. Okay, so these are the four main acids that we're normally concerned with. However, for reasons that we won't discuss here, mainly because it's not reactive enough, hydrofluoric acid does not do this type of reaction. So we're not even going to consider HF. The only three acids we're going to consider for this type of reaction are these three: hydrochloric, hydrobromic, and hydroiodic acid. Okay, the anion of these three strong acids, okay, which is going to be the chloride anion, the iodide anion, and the bromide. These three we typically just abbreviate as X. Normally in chemical literature, when you see X, it's the abbreviation for a halide. In this case, that'd be chloride, iodide, or bromide, excluding fluoride. So when you draw the typical generic acid with X as the anion, you just put H with a bond to X, or you can just simply put HX. This is denoting that this is one of the strong acids whose conjugate base is a halide. Okay, so to look here at the general reaction of hydrohalogenation, we're going to start with an alkene functional group like this. We're going to put it in the presence of one of these acids, either hydrochloric, bromic, or iodic. And essentially what happens is the anion, which would be the halide preferentially gets added on the more substituted carbon. So notice this carbon right here has 2 substituents. The other one, which is over here, only has 1. So we would say the one in green, that carbon, is more substituted, so the halide will preferentially go there. Okay, the other one, which is purple here, okay, this carbon is going to end up with the proton, or the hydrogen there. Okay, and that's the general reaction of hydrohalogenation. So we can look at a specific example here. This is just the general reaction. So we're going to put HX and instead just use the more specific HBr. So notice here, if we look at this carbon, again, this is the more substituted one. So when the reaction occurs, we would expect the halide, which is the bromide, to be added at that carbon. Okay. Likewise, we know that this carbon over here, this one, is actually less substituted, so that's where we expect the hydrogen to go, and that's exactly what happens. Okay. Now, we're going to look at the mechanism of this type of reaction. Before we do that, we need to explore something called carbocation stability. And why exactly is knowing about this important? Well, in general, off the top of my head, at least what I can think, there are 2 addition reactions here where it may become very important to actually draw the mechanism. Fortunately, these mechanisms are actually the most simple. They're the simplest ones in alkene additions. But the reason it can be important is because you have the capacity for something that we discussed in a previous playlist or video called carbocation rearrangement. And carbocation rearrangement is all to do with the stability of a carbocation. So just a very brief review. When you have a methyl, or 0-degree carbocation, that's when you have 3 hydrogens around it, that's very unstable, and things don't like to be like that. If you have this one, which is a primary carbocation, it's still not stable, but it's more stable than a methyl cation. Here we have a secondary. Notice here's one carbon group and here's the other one. So it's secondary, it's more stable than the primary, and by far the most stable carbocation is going to be the one with 3 R groups on it, and that's the tertiary carbocation. So one common sort of motif in reactions where you can have a rearrangement of carbocations is, in other words, if I had the capacity, if I initially generated a primary carbocation, but I somehow had the capacity to get to a secondary, then that's something I would want to do. If I generated a secondary carbocation and I had the capacity to rearrange to get a tertiary, then that will happen. It's spontaneous. And if for whatever reason I generated a primary and I can generate a tertiary from that with a rearrangement, then that will also happen. Going the other direction, say going from a tertiary to a secondary, that's non-spontaneous and it won't happen and you don't have to consider it. In general, the highest degree carbocation, if it can form, is the one that is preferred. Okay, so to understand why carbocations form at certain points, let's run through a few mechanisms, and this hopefully will give you some intuition on hydrohalogenation. So remember here that for alkenes, we talked about the pi bond can act as a base, and that's what happens. These electrons come out and abstract the hydrogen from the hydrobromic acid, generating this bromide anion. And the question is, why does the carbocation form there? Well, the reason it forms there is because notice that this carbocation is actually, technically, it's tertiary, right? Has one carbon there, and one carbon there. This one, if it actually formed here for whatever reason, it would only be secondary, which isn't as stable. So that's why the hydrogen goes on this carbon and the carbocation goes on that carbon. Okay? So now we have a good electrophile. A good nucleophile is the bromide. So the bromide will attack or capture the carbocation, and it's going to form a bond right here, and this is your product. Okay? So again, why did the carbocation form here? Because it would be tertiary if it formed here, but if it formed on the other position, it would be secondary, which wouldn't be good. Okay? Here's another example. Let's use HCl. That's another hydrohalic acid we can use. Pi bond again here is going to act as a base. It's going to abstract the proton from that hydrochloric acid, generating the chloride. Now the question is, again, why does the carbocation form here instead of here? Well, keep in mind, if the carbocation formed here, which it did, it's actually a secondary carbocation. If it actually formed here, it'd only be primary. So that means it will preferentially form at the highest degree carbocation, and then there won't be a rearrangement, and then we can get chloride to attack there at the carbocation, and that's why chloride forms here and hydrogen goes at the other carbon position right there. Okay, so hopefully that's making a little bit of sense. Now, the reason it's important to draw the mechanism on this reaction and then one other, which is hydration of alkenes, is because for those two reactions, you can be susceptible to rearrangements, i.e. this reaction right here. So here's what's going to happen. Again, the pi bond is going to just take this proton from the hydrochloric acid, as we would expect, and initially you generate a carbocation right here. But notice, and I can even draw it in right here, there is a hydrogen or a hydride right there. I've drawn it in right here already. So if I have this carbocation right here, what's the degree of that? Well, that one is a secondary carbocation. Now, if I were to shift this hydride over one bond, in other words, if I were to move it right there, which it will, then what would be the carbocation that forms here? Well, it has 1, 2, 3 R groups. So this one is actually tertiary, and that's more stable. Okay? So now I have the carbocation at arguably the most stable position. So now the chloride will actually attack that carbocation, and it will form the bond right there. Okay? And it turns out that you can get some attack on the secondary carbocation, but the major product, let me indicate that this is the major product, is going to be with the rearrangement. In other words, where the carbocation rearranges and then the nucleophile attacks. Okay? Now, in some of the later reactions that we're going to do in a few videos, they tend to have a very specific stereochemistry that they produce. They either do their mechanism in a syn addition fashion or an anti, usually one or the other. There are a few reactions, though, that we're going to do initially that they are not what we call stereoselective. If something adds in an anti-fashion or it adds specifically in a syn fashion, which we discussed in a previous video, then we would say it is stereoselective. However, Because this reaction, as we'll see, does not add specifically syn or anti, it can actually do either, it is not stereoselective. Okay, and we're actually going to look briefly at why it is stereoselective. So just keep in mind what we've been doing. We start with this alkene functional group, which comes out and plucks off a proton, and then we end up generating a carbocation at the more substituted position. Okay, so here's what I've done down here. I have these two alkenes, this general alkenes, one shown up here, another one shown down here. These are the exact same alkenes we're going to assume for the second. They're the exact same alkene, but notice R1, R2, R3, same thing down here. They're the same molecule and in exactly the same orientation. The difference of what I'm going to do here is I'm actually going to put the hydrohalic acid below the alkene on top. On this bottom one, I'm going to put the hydrohalic acid on top of the alkene. Okay, so in other words, the proton that's going to be added first is going to be on a different side of the vertical axis of the molecule. So what's going to happen first? Well, in this first case, notice the alkene would come out here, its pi bond would attack the proton, abstract it. And in any case, what you would get is you get this molecule that's shown right there. Okay, but notice this proton I put in purple, right? And to show you that the proton that would be added would be sort of be coming down from this R group. It'd be beneath the plane of this molecule, okay, down here. Now, another thing I could do is I could put the acid on top of the molecule. Pi bond's still going to come out and get that proton, right? But in this case, notice I put this proton in blue. So that means because it's attacking the proton up from the top, that proton, which is blue, would be right there on the top. It'd sort of be coming up above the plane of this carbocation that's generated. Okay, so number one, depending on from what orientation the proton transfer occurs, the hydrogen can be added either on bottom or the top, okay, depending. Now remember that we've now generated a carbocation. This carbon right here, this carbon, let me show this in a box. This carbon is, it has positive charge, but it also, remember, is devoid of an octet, okay? Remember, there's 2 electrons coming from this bond, 2 electrons in this bond, and then 2 on this one. So it has 6 valence electrons overall, which isn't good. Carbon would like to have a total of 8 electrons total to satisfy its octet. So in other words, it's devoid of an octet, making it exceptionally electrophilic. The other thing also about when you have a carbocation is it has sp2 hybridized geometry, meaning that it's planar, it's flat. So if you were to think about a sheet of paper, if you hold a sheet of paper flat, just hold it up in the air or something, you could imagine that there's an equal likelihood for air molecules, say, to hit it from the top and also to hit it from the bottom. Can do either one, right? So that means that by analogy, the nucleophile, which is the halide right here, can have virtually an equal likelihood of attacking the carbocation from the top, or it can attack the carbocation from the bottom. And I've shown both possibilities here. And what you essentially see is when it attacks from the top, you ultimately get the halide attached right there. But if it attacks from the bottom, I've shown that it attacks right here. Okay? And ultimately what that does is whatever the stereochemistry is of this carbon, say it was R stereochemistry, then that means this carbon down here, because it attacked from the opposite side, would actually have S stereochemistry. Okay? So what's the point? Well, the hydrogen right here can add top or bottom. The halide, because of the carbocation, can add top or bottom, which means that overall this process is completely non-stereoselective. You can't select which enantiomer or diastereomer forms. You get a mixture of products. However, because this reaction is what we call a Markovnikov addition, the halide will always add, in the more substituted position. Okay, that's something you can pretty much guarantee. All right, so here's what I have here. I have some practice problems, okay? All right, so I have some practice problems right here. These ones on the top, I'll just go ahead and tell you there is no capacity for carbocation rearrangements. These two down here that I have, there is capacity, and so for these we'll draw the mechanism. Now you should get familiar with drawing mechanisms in general, but that could be something with these that you practice on your own. Here I just want to focus on figuring out preferentially where the halide is going to add. Okay, so look at this molecule. Here's the alkene right there. Which position will it add to? Well, this carbon, notice, has two substituents. This one over here has one. So that means the bromide is going to add to the central carbon right there. So my product should look something like this. Okay, bromide should add there, and then the hydrogen should add right there. Okay, again, if this were chiral, and it's not, it's a meso compound, you wouldn't really have to worry about indicating stereochemistry because of the mixture of products that form. Okay? Here's another example. Here's my alkene. Which one of these carbons does the bromide add to? Well, it's going to add to this one because this one has no substituents other than hydrogen. This one has two carbon groups. Okay, so it's going to add to this carbon that's actually part of the ring. So what's my molecule going to look like? The bromine is going to add right there. And unless there's stereochemistry, you really don't ever have to indicate this hydrogen. We can if we want to. Just know there is a hydrogen right there, but there's also two others there. But that's up to you whether or not you want to indicate it. The main thing you want to indicate is the bromide that gets added. Okay? Here's another example. Here's another alkene. It's essentially an isomer of this compound, right? And where does the bromine add? Well, let's just do a different color. This position has two carbon substituents, and this one down there only has one. So it will add to the position where I dotted it. Okay, so that means draw the compound, and it will also add to this position again. So we actually get the same compound twice for two different reactions. Okay, do another example over here. Right here we have the alkene right here. If we look at the top carbon, we see it has one substituent over here. On the bottom carbon, it's going to have two substituents. Therefore, that's the more substituted carbon, and that's where the chloride is going to add. So we can draw this product like this, methyl group, and then a chloride right there. There's our product. Another example. Let's look here at this alkene. Here's our double bond right there. Clearly, the right side, this carbon has no substituents, only hydrogens, and the only substituent is on this carbon right there, the left one, so that's where the iodide is going to add. So we can draw the product like this. Okay, there you go, and you can even draw the hydrogen over there if you wanted. Okay, going to the next example, the last one where we're just predicting simple products. Look here, here's the alkene in this molecule right there. If you look at this side, there's one substituent on the right carbon. On the left one, there are actually two substituents. So we're going to say that the bromide is going to add preferentially right there. And so we'll look at the product. I know I have the arrow down like that. I'm just going to draw it right here. You'll see why in a minute. So here's the carbon skeleton that doesn't change. And then we have the, in this case, a bromine or a bromide that's added right there. Okay. So that's just a series of sort of predicting the products whenever there are no carbocation rearrangements. And what I challenge you to do is definitely go through these examples and draw the mechanism for how they add. These two examples I'm going to do right here, there actually are some considerations that we're going to have to take in terms of carbocation rearrangements and so forth. So for these, we're going to actually practice drawing the mechanism. Here I have this alkene. Okay, the double bond, the pi electrons are going to come and pick off that proton from hydrobromic acid, in which case I'm going to end up with this intermediate right here. So note that the proton is going to go right there. That's the hydrogen that comes from HBr. And initially I'm going to generate a carbocation right there because that's the more substituted side. Okay. This carbon is more substituted clearly, but also realize that I actually have a hydride right there. There's a hydrogen off of here because this carbon only has 3 carbon bonds. Okay, so actually this right here, this carbocation is technically secondary. If I were to move this hydride right there to attack the carbocation, then what I would generate is a carbon with 3 bonds, and it would be a carbocation. Therefore, it would be tertiary. So drawing the next mechanistic step, okay, I would have this right there and a carbocation at this position. And again, this one is going to be a tertiary carbocation, a much more stable one than a secondary. Then I can have the bromide that was generated. Okay, again, it has 4 lone pairs. I'm only indicating 1. And then the bromide will come over here, capture the carbocation, and then I will actually end up with the final product. So this will be right there, and then a bromine or a bromide on that carbon. Okay, and again, that's due to the hydride shift. Okay, one more example. Let's use hydrochloric acid. I have a double bond right here, so this can come out and pick off that proton from hydrochloric acid. Okay, simple proton transfer. So then I'm going to end up with this molecule. Again, this carbon right here, this carbon is clearly more substituted, so it's going to be the one that ends up with the carbocation. Again, just to designate the order of this, 1 carbon here, 1 group over here. That means this carbocation is secondary, but also remember over here I have a hydride off of that because this carbon right here has 3 carbon bonds. So what I can do is I can take this hydride and move it over here. The question again I always ask myself is, can I take a secondary carbocation and make a tertiary one using a rearrangement? That's sort of the logic that we used way up here, if I can find it, when we were discussing carbocation stability. Go from primary to secondary, secondary to tertiary, or sometimes primary to tertiary. Okay, let me go back down to the mechanism. Okay, so I can take this hydride, move it over there, in which case the molecule that I get is with the carbocation here, and I can designate the order of this carbon. It's a carbocation and it's tertiary because it has 3 carbon groups. Okay, then again with the initial proton transfer I freed a chloride anion. Okay, that's going to be the active nucleophile. It's going to come and attack the carbocation, capture it, and then I'm left basically with my final product with the chloride attached there. Okay, so again on these types of problems where you're doing hydrohalogenation, sometimes if you have time on your exam, or at least you know that you have time, it's actually useful in this type of reaction to draw the mechanism, because in general you can see they're not really that complicated relative to some of the other ones we're going to see later on in this chapter and other chapters. They can get very, very convoluted, and so it might not be beneficial to draw those for the sake of time. However, for this one, and then there's another one we're going to look at called hydration of an alkene. That's another one where drawing the mechanism could come in handy. For other ones, you're just going to want to focus on predicting the products and understanding the concept. But for this one, and then also hydration of an alkene, you have the possibility of a carbocation rearrangement, and that is something you have to worry about. Again, the only other concept I wanted to note is back what we talked about up here before we started doing the practice. Remember that depending on the orientation of the acid with respect to the alkene, the hydrogen can be added on either the top or the bottom face of the alkene. And then also because you generate a carbocation that's planar, there's about approximately an equal probability that the nucleophile, the halide, can attack also from either side and add to either side. So you end up with a mixture of products, and therefore hydrohalogenation is not stereospecific. Okay, so hopefully this made a little bit of sense. In the next video, we're going to look at hydration of an alkene, and then after that, we're probably going to look at a similar hydrohalogenation reaction, but with a radical mechanism. And that's going to use a peroxide, but it's actually not going to give us a Markovnikov addition as shown here. It'll give us an anti-Markovnikov. So thanks again for watching. Please like and subscribe to this channel. Thank you very much.